Hi everyone. So let's begin our class for electromagnetic, right? So this class is going to be for electrical engineering and for ECE as well, right? So whatever topics are there for electrical engineering and for electronics and communication, everything I'm going to talk about that, right? So primarily I will be focusing on electrical engineering. That is one of the basic thing we need to cover up, and then we will go to the syllabus of electronics engineering, right? Okay. Yes. Hi Surajit. Yes. So the topic which we will take up, throughout our session will be what? Let me tell you the topic which I'm going to take up is the very first topic which we'll be taking up is the vector analysis, right? Where we will talk about vector calculus basically, right? That is the prerequisite for electromagnetics, right? So vector analysis. So you can take down the topic here. And second topic which I will be discussing is after finishing this, that electrostatic field, right? Electrostatic field. Okay. And the third topic we will take up is magnetostatic field, right? Magnetostatic. Okay, magnetostatic field. And the fourth one is going to be very important, in fact, for electrical as well as electronics student, that is boundary condition and Laplacian. So boundary conditions and Laplacian. Okay. Poisson equations and Laplacian equations, right? And Laplacians. Laplacian equations, in fact, Poisson equations is used, to derive many equations of p-n junction and all. If you want to analyze electronic devices, so you always go for Poisson equations, right? So we need to understand, we need to get familiar, make ourselves familiar with the Poisson equations, so that these sessions will be helpful to understand electronic devices as well, right? So all the subjects are interlinked, So the fifth one is gonna be the very important equations, which has created revolution in our life. They are the Maxwell equations. Okay, they are the Maxwell equations. So we will talk about them. The Maxwell equations. Okay, four equations. The Maxwell equations in integral form uh, as well as the differential forms, right? So Maxwell equations are very important. Directly questions are asked in different PSUs and IES and gate examination, right? They will give in the four options one Maxwell equation, and they will ask which one is going to be correct, right? So the Maxwell equations are very important, in fact, help you determine or analyze various phenomena of electromagnetics. And the sixth topic which I will be teaching you is uh, the uniform plane wave, right? So uniform plane wave, okay? Uniform plane wave. So these are the topic 1, 2, 3, 4, 5. Okay, these are the topic which is given, in fact, in the electrical engineering syllabus, right? E syllabus. And from the sixth topic, that is uniform plane wave, electromagnetic waves, uh, that comes under ECE paper, right? So, but in order to understand uniform plane wave, and in future topics such as we will be talking about polarization and reflection and refraction, right? Polarization is one of the very important topic for ECE, right? Polarization and reflection and refraction. Okay, reflection and refraction. Okay, so whenever electromagnetic wave will go from one medium to another medium, right? So what will happen? Or whenever it incident on uh, a certain interface, what kind of phenomena happens? Okay, so that is seventh topic, and the eighth topic is going to be the transmission line. So these are the application of electromagnetic, right? Transmission line. Okay, transmission line, that is important for EC paper, right? EC. And next one is going to be your waveguides. Okay, so we will see what are the differences basically between transmission line and the waveguide. And the last topic of the discussion is going to be the antenna. Okay, antenna, right? So this is our course outline. Okay, course outline. Right. So the vector analysis, which is the vector calculus, you can say, is the prerequisite for entire electromagnetics. You should be good at differential equations. You should be good at integral calculus as well, right? Anyway, so let us begin. See, I'm not going to discuss about what is vector and scalar, because the differences and the quantity, any physical quantity, can be described with the help of vector and scalar, right? So you must know all these things. So I'm not going to discuss what is vector. Already everyone knows what is vector and what is scalar and what is tensor, right? So we will start directly from the coordinate systems, right? Three-dimensional systems. Okay. So yeah. But before that, we can write the definition of electromagnetic waves. What is the meaning of electromagnetic waves, right? So you can write the definition of electromagnetic waves, right? Why we need to talk about coordinate systems and all. So from the definition of electromagnetic wave, okay, after all, we will be talking about electromagnetic waves, so you have to understand, right? So what is wave basically? A wave is basically a physical phenomena, right? Okay, which reproduces after a certain amount of time, okay, at some other places, right? So this electromagnetic wave will depend upon the time, okay, and the space variable x, y, and z, right? Okay, so because of to understand electromagnetic wave phenomena, as well as to understand entire electrostatic and magnetostatic, okay, we need to introduce coordinate system, okay, coordinate system, or to analyze any kind of structure. You will find in your real life, you will find the structure like cylindrical structure. You will find the spherical structure, right? So to analyze them, right, suppose a waveguide is there, right, rectangular waveguide. Okay, so which coordinate system is going to be useful? Okay, so all those things to be analyzed, we will first discuss about the coordinate system, right? So the topic of today's discussion is going to be the coordinate system. Coordinate system. Okay, right. So please, you might be familiar with what is vector and scalar, right? And what are the difference between them, right? So vector is basically a quantity which is having magnitude as well as the direction, okay, and the scalar is having only magnitude, right? Okay. So coordinate system, in coordinate system, if I talk about, there are two-dimensional coordinate system, right? You can say two-dimensional coordinate system, two-dimensional, and you can also say three-dimensional. So I'm going to focus on three-dimensional, right? Three-dimensional coordinate system, right? Okay. So the in two-dimensional coordinate system, the first one is going to be your rectangular coordinate system, right? Rectangular. Okay, rectangular coordinate system, and second one is, or it is also known as Cartesian, right? It is also known as Cartesian coordinate system. Cartesian, right? Cartesian. And second one is going to be your okay, which you might have studied in your school days, that is polar, right? Polar coordinate system, right? And in the in 3 dimensions, we will talk about Cartesian first, or rectangular, you can say, right? Cartesian. So here the coordinates will be x and y, okay, and here the coordinates will be x, y, j, right? 3 coordinates. But in case of Cartesian, x, y, z, in case of cylindrical, in case of spherical, the coordinate, the parameter will be different, right? So Cartesian, okay, second one is gonna be your cylindrical, right? And third one is going to be your spherical, right? So depending upon the application, we will be taking the help of these coordinate system. Okay. So the first coordinate system which I'm going to talk about is the rectangular coordinate system in 2D, right? So in two-dimensional, right? In two-dimensional, the in 2D, right? Okay. So suppose this is your x axis and this is your y axis, okay? So any point, if we want to locate here, that is the point P, you can say, okay? So this point P is there, okay? So this point P, if you go in the direction x, right? If you're going in the direction x, this point P, if you go to x direction, okay, yeah, and you will cover the distance x, and if you will go toward y axis, right? So you can meet this point here. That point is located here, right? So you can say that this point is having x y coordinate, okay? And also you can write you can tell the direction unit, you can say unit vector, right? So if you are going in the by direction, right, so in this direction the by is increasing, okay, and in this direction the x is increasing, okay. So this is the point P, can be located in the two-dimensional plane, okay. This is a x plane, x axis, and there is a y axis. So in x axis the y equal to 0, right, and in the y-axis the x is going to be 0, okay, and this is the origin here, okay. So in the two-dimensional, you can locate any point in xy plane, okay, right, and this is what the a by cap, and this is a x cap, right, okay. So any vector, suppose any vector p is there, any vector p will be there, right? So how can you write p here? So p will be having the px, you can say, okay, sitting along what, sitting along x, okay, plus p by sitting along a by, right? This is what the vector is. The p vector is having the magnitude, that is px, and the direction p by and the direction, right? Okay, so this is how we can locate any point in the two-dimensional plane, right? Two-dimensional, okay. So on x, if I talk about x axis, okay, so your y can range, see, your y can range here from minus infinite to infinite, and your x, if I talk about range of parameter, right, so your x can go from minus infinity to infinity, your y can go from minus infinity to infinity, right? So anywhere, if you will put, anywhere you put your pen, right, there would be one coordinate system, right? So anywhere you put, right, suppose here we are putting, so this is our x and y, right? So this there is a freedom in this coordinate system, right? So remember that in Cartesian coordinate system there is no restriction, right? Anywhere you can locate any point, the coordinates are same, right? The direction will not change, okay. So ax cap is the unit vector along x-axis, and ay is the unit vector along y-axis, right? So ax and ay are the unit vectors, and remember they are orthogonal to each other, you can see, right? They are orthogonal to each other. So these coordinate systems, okay, follow orthogonality. See, you can see here the x and y are kept in such a manner that they are having they are orthogonal to each other, right? So here x and y, you can write here as well, the x and y, right, are orthogonal, right, to each other. orthogonal to each other. Okay. So Cartesian coordinate system and in fact the coordinate systems, which is a tool to analyze entire electromagnetic. So please focus here, and we will talk about various theorems in the vector calculus, right? That is also going to assist us to understand many topics, right? Okay, so these are what ax and ay are orthogonal to each other. They are the unit vectors, right? And they are represented along x-axis and y-axis respectively, right? Okay. And also, if I talk about the magnitude of them, so any unit vector has having the magnitude 1, any this is the basics everyone knows, right? And second one, which I'm going to talk about, is the polar coordinate system. Polar coordinate system. Okay, system. In the polar coordinate system, again the same story. Okay, we have to take the help of Cartesian coordinate system only. This is x-axis and this is y-axis. Okay, and we have to take one circle, right? So this circle will be there. Let me draw this circle properly. Okay, there is a circle, right? Okay, and there is a point P we will take on the circle itself, right? This point P will be there. Okay, and we have to draw we can find the relation between polar and Cartesian, but for the time being, we will join this origin, okay, from this point P, and we will say that this is a rho. Okay, rho, and this line which is joining from origin to this point P is making an angle from x-axis, that is phi. Okay, so this coordinate is what? This coordinate is going to be rho phi. Okay. Right now I'm just talking about two-dimensional, but we will only discuss about what? We will only discuss about three dimensions. In fact, apply, okay, the concept of three dimensions, because our electromagnetic wave will be propagating in the space. Okay, right. So this phi is being taken from the x-axis. Okay, so this phi is increasing. You can see here this phi is increasing in this direction, right? So this is our unit vector a phi. Okay, and this rho is increasing in this direction. So you can say that a rho. Okay, this is the unit vector along a radius rho, right? This rho is the radius here. Okay. So now we can discuss about the um, locus of rho. If rho is going to be constant, okay, so what kind of locus you're going to get, right? So if rho is constant, you can see here you will get the circle, okay, whose center coincide with this origin, right? Whose center coincide with origin. So let me write here all these parameters for two dimensions. Then we will start the three dimensions, right? Okay. So if rho is constant, right? If rho is constant, if rho is constant, what does it give? The locus of rho is constant will be, locus will be what? Locus will be, locus is gonna be your circle, right? Circle. Okay. Locus will be circle here. You can see as well. And your phi will vary from what? Your phi can go from, you can just get back. Your phi can go from what? Your phi can go from x to like this. So from 0 to 0 to 2 pi, right? Your phi can range from 0 to 2 pi. Phi can go from 0 to 2 pi. Okay. This is very important. Please keep this in mind. If rho is constant, the locus is going to be your circle, and your phi will be ranging from the possible, all possible values for the phi, will range from 0 to 2 pi. Okay, and a phi and a rho, a phi, this is a phi and this is a rho, right? They are the unit vectors and are orthogonal to each other. You can see anywhere you put take point here, if the rho is constant, right? Anywhere. So now you can see the phi direction and everything will be changing. Okay, now the rho is A rho is pointing like this, and your phi direction is like this, okay, A phi. Okay, so if you will take point on this circle at a different point, right, at a different places, right? Suppose you are locating some point at this, okay, from the origin, so the direction is going to be changed, right? So there is a restriction on polar coordinate system, right? Okay. So if I want to talk about the relation between uh, Cartesian and polar, right? Relation between Cartesian, right? Cartesian and polar. So suppose x and y are given, and you have to find rho and phi. So how can you find? So let me draw here again the circle, right? So this is a circle, right, of a rho constant, and there is a point P. Okay, so draw the perpendicular from this point P here. Okay, so this will be x. Okay, and this is x-axis, and this is y-axis, right? And draw the perpendicular from this point as well, right? So this is the y, okay, from here to here, and join this point, okay, and there is an angle phi. Okay, there is angle phi. Okay, so this is rho phi, or you can say xy as well. Okay, so now you can find what is going to be rho. Rho is this, right? So can you find rho? This is by, okay, this is by. From here, the relation which we are getting here is from Pythagoras. Okay, this is by, right? By. So the rho is going to be what? Under root x square plus y square. Okay, you can write directly rho. Rho will be what? The relation between Cartesian and polar is going to be rho. Rho will be what? The x square plus y square, or x equal to, you can say x is going to be what? X will be rho cos phi. Okay, rho cos y, and the y will be rho sin phi. Okay, rho sin phi. Okay, so this is our first equation, this is our second equation, and if you're going to take the square of them and add, okay, so you will get what? Rho equal to x square plus y square, right? So you can say this is 3. And now how can you find phi? So just take the ratio of equation 1 and equation 2. So you will get here that phi will be equal to tan inverse, okay, tan inverse by x. So these are the relation you have to keep in mind. The first is what? The first is x equal to rho cos phi. The second one is y equal to rho sin phi. Okay, and third one is rho equal to what? Rho equal to x square plus y square, and fourth one is phi is going to be tan inverse by x. So how we are getting? I have told you. Okay, so this is all about two-dimensional, right? So you have to keep this in mind. Okay, now you can see here this phi direction. How can you see this? How can you see this phi direction? Where is the phi direction? Phi will be changing like this. Okay, so you can say that in fact it may be thought also of the tangent to the circle, right? This a phi can be tangent to the circle. Okay, this is a tangent, right? If you draw this one line, so if that phi direction is changing, you can say as a tangent to the circle, right? Okay, and this arrow can be seen like if you are drawing the normal to this tangent. Okay, drawing normal to the tangent. Okay, so a rho is represented as normal to rho equal to constant. Okay, or normal to this circle. So anywhere you draw, like this is a rho. Okay, and this is gonna be a phi. D are the unit vector we'll locate. Yes. Now, so we have seen this is what now we will talk about three-dimensional, okay, coordinate system. Three-dimensional coordinate system. That is 3D. Okay. So what is plane basically? We are talking about plane, right? We are talking about plane. So what is plane? Uh, like we discussed about 2D plane, XY plane, right? And where we located one point, and that point P was having coordinate X and Y, and X was ranging from minus infinite to infinite, and Y was ranging from minus infinite to infinite. But in this case, if rho is constant, okay, so your phi can go from 0 to 2 pi. Okay, so this is the all possible values for the phi. Okay, and this will be used in case of antenna. Okay, in case of any vector calculus problem you are solving. So mainly in case of differential length, right? When you will integrate d phi. Okay, so this the limit of integration. Okay, will be taken care of by these limits, right? 0 to 2 pi. So all possible values, right? Remember. So this is the range, right? So what is plane? What is plane? How you view as a anything as a plane? So plane is basically nothing but a seat-like structure, right? A plane is nothing but a seat-like structure. So now we need to visualize three-dimensional plane, right? Three-dimensional coordinate system, right? So we will see various planes, and we need to visualize as well. A plane is a seat-like structure. Is a seat-like structure. Okay, whose thickness is negligible, right? Whose thickness is negligible. Thickness is negligible, right? Is negligible. Okay. So what is plane? Plane is basically a seat-like structure. Just you take one paper, right? That is going to be your plane. Okay. Just because the paper also does not have any thickness, right? So the very first coordinate system which we will talk about here is the Cartesian coordinate system. Cartesian coordinate system. Okay. So if I talk about xy plane, right, in the Cartesian coordinate system, we will see these coordinate system will follow basically the right-handed system, right? Right-handed, okay, right-handed rule you can say, right-hand rule you can say, or right-handed rule, right? So just forget about this right-hand rule means we will go, suppose this is x-axis, then this is going to be your y-axis, right? So if I talk about xy plane, so this is basically the xy plane, right? This is basically the xy plane, okay? Remember, this is a xy plane. Let me draw this, okay, this line so you can visualize this is your xy plane, right? In two dimension. In two dimension, this is your xy plane, okay, which looks like a seat, which looks like a seat. And where x is ranging from, okay, this guy is xy plane, and this x is ranging from minus infinity to infinity, okay, and y is also ranging from x, okay, I mean from minus infinity to infinity, okay. So this is the seat, okay. Now in case of Cartesian coordinate system in three dimension, what we will see here is that this is going to be your three dimensions, right? This is x-axis, this is y-axis, and this is z. So any point if you want to locate or capture, okay, with the help of Cartesian coordinate system, okay. So anywhere you will put that you know tip of your pen, right? Suppose you are putting, suppose there is a point P here, right? So what is the coordinate system of this? Okay. any point if you want to locate in 3D, so what should be the coordinate system? Okay, so but before that we need to define the plane, right? So this is xy plane, right? This is xy plane in 3 dimension, right? So this is xy plane, right? This is xy plane. Let me draw here, and this is the yz plane, right? This is yz plane. Okay, and so this 3-dimensional is what this 3-dimensional is basically having 3 planes. Okay, so this is going to be the picture, right? So you can see this is a yz plane, and this is what the xz plane, right? This is xz plane, and this is what orthogonal system, right? Because x and y and z are making 90-degree angle. Okay, uh, okay, so you have to keep this in mind, right? This is there is a 190-degree, sorry, 90-degree angle is here, and this, okay, this is how we make, right? So this is your xy plane. In xy plane, what is 0? In xy plane, the z is equal to 0. Remember, this is your yz plane. What is fixed here? The fix is x equal to 0, right? In yz plane, if I say x equal to 0, so you have to accept it, right? In zx plane, or you can say in zx plane or xz plane, right? What is 0 here? That y is equal to 0. So remember that, okay? So this is how we talk about the planes in 3 dimensions, right? This is the planes. Now it looks like a plane, right? Okay. Let me join these lines as well. Yes. So this is a 3-dimensional structure now. Okay, it looks like a cube. Okay, some colored cube, right? So we are talking about these 3 planes, and this origin is basically the intersection of these 3 planes, right? You can see there is an origin. Okay, and if you are in x-axis, so the y is equal to 0 and the z is equal to 0. Okay, here the two coordinates are fixed, right? These are fixed. Okay, these are fixed. In plane, only one coordinate is fixed. Okay, this is fixed. So what can be varied? The x and y can vary. Okay, so that is giving you the plane, right? If two points are fixed, so what it is giving? It is giving you the line. You can see it is giving you the line, right? It is giving you the line. And if one point is fixed, so it is giving you the plane. If all the 3 points will be fixed, then it will give you only 1 point, right? All points are fixed. X equal x and y and z all 0. So they are fixed. Right? So that is going to be the locus, right? Locus of fixing different points, coordinate systems. Okay. So you have to keep this in mind. If you are in x-axis, so y equal to 0 and z equal to 0. If you are in y-axis, then x equal to 0 and z equal to 0, right? And if you are in z-axis, what is going to be 0 here? X equal to 0 and y equal to 0. So all these things are very basic, okay, which will be helpful. Okay, yes. So let us go to talk about locating that point in 3D. So this is our z-axis and this is y-axis, right? And this is going to be your x-axis. Let me raise these things and let me take lines. Okay, so this is our y-axis and there is going to be z-axis, okay? And this is going to be your x, right? So this is x, this is y, and this is z. Suppose any point P is here, right? Any point P is there, right? P. This point P will be having the coordinate as x, y, z, right? If you are in Cartesian coordinate system, right? So what you can do here is that you can draw one projection. I mean, this P point can be projected here in the xy plane. You can say P dash it is. Okay, it is a P dash, and So you can join now this point, okay, from this x-axis. You can draw this one perpendicular, okay, and you can also draw perpendicular from this point P dash to on the y-axis, okay, right? And this is what the you can join from the origin, right? Okay. So now you can see here this will be the unit vector along z direction, right? Az cap, okay, and x is increasing in this direction, right? So you can say this is your ax cap, and your by is increasing in this direction, so you can say that the by will be here in this direction, right? So this is a point P, right, which is having x by z, okay. And what is the coordinate of P dash? P dash will be here, that in xy plane z is going to be 0, right? Z is going to be 0, so only you will be working with 2D, okay, 2D plane, okay, 2D plane, right? So this will be joined from here to here, right? So there is a plane, one plane, right? So this is your jet. This is the jet here. So this point can be located with the help of 3 dimension. Okay. So this is how we locate point x, y, z. And now we can talk about the range of parameters. So range of parameters is going to be what? Range of parameter. Range of parameters, so x can go from minus infinity to infinity, the y can go from minus infinity to infinity, and z can range from minus infinity to infinity. Okay, so there is no restriction. You place anywhere the tip of the pen, you can decide the coordinate system, right? Suppose I'm putting here, so there is a, okay, this is z, there is a y, and there is x. I'm putting here, there is a z, there is a y, and there is, you know, so in Cartesian coordinate system there is no restriction, okay, no anywhere you can locate, but the coordinates, the direction is going to be same, right? The unit vector will be same always, okay. The magnitude may differ, but the unit vector will be same, okay. Direction will not change, okay, right? Any rectangular shape or any kind of shape you can analyze with the help of Cartesian coordinate system. So you will use these coordinate system in case of waveguides, okay, waveguides, right? That is going to be range. And locus, I have, as I told you that uh, we have fixed 1 point, 2 point, 3 points, right? So you can write here as well. So in general, in three-dimensional coordinate system, right, fixing 3 coordinates, it will give you the point, right? In general, fixing 3 coordinates, okay, what you will give, you will get the point, right? Okay, if you will fix 3 coordinates, okay, so you are going to get point. And fixing 2 coordinates, okay, fixing 2 coordinates, okay, what are you going to get? If you are going to fix 2 coordinates, you will get line, right? Line. And if you're going to fix 1 coordinate, right? Okay, fixing 1 coordinate, what are you going to get? That these are the locus which you will get, right? You will get plane. Sometimes question is asked in HAL or any examination, right, from the coordinate system. So this kind of question may be asked, right? Fixing, if you are going to fix, what is the meaning of fix? Fixing means that 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 coordinate cannot be changed, right? Only suppose we are in the xy plane, so we can change, we can we can see the range of xy where up to which range it can vary from minus infinite to infinite, right? So please keep this in mind. These are the locus. These are the locus, right? Okay. I hope this is clear for everyone. And unit vectors are like ax cap, ay cap are the unit vectors, and they are orthogonal to each other. You have to keep this in mind, and they are represented along x-axis. Okay, so they are represented along x-axis, right? There will be a ax cap in this direction and in this direction. So here you can see this is by x cap, okay, and this is az. They are the unit vector and they are orthogonal. Okay, they are orthogonal to each other. All right. And they may be also represented as unit vector normal to x equal to constant. Okay, so if that x equal to constant, what is the meaning of that? X equal to constant means you are in bi-z plane, right? Okay, so remember these things: bi equal to constant and z equal to constant planes respectively. Okay, x equal to constant planes means what is the meaning of this? Which plane we are talking about? So I'm talking about bi-z plane. Okay, so in bi-z plane, x is going to be, so y is changing like this and your z is changing like this, right? So this is a plane basically. This is a plane, right? This is a plane. What shall be the the direction of this plane? Okay, so this will be directing like this. Okay, so this is the x normal, right? Remember, so these things will be utilized when we will discuss about differential area. Okay, differential area, because after all area is also the vector quantity. Area is a vector quantity, right? Okay, many people consider the area is not the vector quantity, but yeah, in practice the area is a vector quantity, because they always study in school days that the area of the circle is pi r square, and there is no direction, right? But yeah, that direction will be normal to the surface, right? So we always write the area, magnitude, and the direction. So remember that area is a vector quantity. We will talk about that differential area and all. Now let's talk about second kind of coordinate system, that is the cylindrical coordinate system, right? What is the need of cylindrical coordinate system? Okay, see, we will find in our real life different kind of structures. Suppose we have got the cylinder. Now we need to analyze that. Any shape, okay, any shape which looks like a cylinder, okay. So there we can't use Cartesian coordinate system. So we can use Cartesian coordinate system, but the thing is the analysis is going to be very complicated, right? So then we need to recall the cylindrical coordinate system, because that is going to be coming handy to analyze. Okay, so remember, so any shape which is having symmetry, cylindrical symmetry, okay, can be analyzed with the help of cylindrical coordinate system, right? Okay, so what we have to now do here is we have to cover the space with the help of cylinder. So this is cylinder here, right? Now we are covering the space with the help of cylinder, right? Okay, so we can put the axis now. The cylinder axis will be x-axis. Okay, the cylinder is kept along the x-axis. This is y-axis, not x-axis. This is z-axis basically, right? We have to follow this only. This is x, this is y, and this is z. Right hand rule. Okay, we are going from x to y to z, and this. So now the cylinder is kept along z-axis, and this is y-axis, and now this is going to be your x. Okay, so this is a cylinder. Okay, now we need to locate one point on the cylinder, right? So how? Okay, so what are the coordinates we are going to get? Okay, so remember that, let me draw here properly. So this is the x-axis, x by g, and put the cylinder here, one cylinder. Yes, this is cylinder, and try to locate one point P on this. This is point P. Suppose this is a point P, right? Just take point P here. Okay. And what you can do now here is you can project this point P on the xy plane. So this is a point P dash, right? And the line which will be joining with the origin, okay? The distance from the origin to this point P dash, that is projected 1, okay? So what we are doing here is we are taking this point P and we are taking the projection of that on xy plane. So this point P can be taken anywhere, right? On this circumference of this top circle of the cylinder. And remember, the angle which it makes with the axis is gonna be phi. So let me erase this again and write properly. Yes. So you can see here the line joining this is rho, and the angle which it makes with the x-axis is phi. Okay. So the first coordinate is going to be rho, second is phi, and the third is we are going along the cylinder, right? So you can see here we are coming from here to here, right? So this is the you can see from here to here the z-axis will be, right? I mean z. So this is rho phi z. Okay, so this point P can be represented as rho phi z, right? So the parameter for cylindrical coordinate system will be rho phi g. The parameter for Cartesian coordinate system was x by z, right? But in this case, the parameter is going to be, this is the parameter for cylindrical coordinate system. Okay. So what we have done here is we have taken one point P on this cylinder, so circumference of the cylinder, and we have taken down the projection, right? Now we can see the relation between Cartesian and cylindrical coordinate parameters. Okay, what are the relations? So let me draw here again the x. Okay, this is y and this is z. Okay, and there is a P point P, right? This is a point P which is coordinated as rho phi g. Okay, and let us take the projection of this guy. So there is a projection P. Okay, P dash. Okay, so this is rho and this is phi. So what you can do now here is you can draw the from this P dash you can draw the perpendicular here. So this is y, and you can draw the perpendicular. So this is x, right? So now we can find the relation. Okay, we can find the relation. Okay, this is rho and this is z, right? So we can take two-dimensional xy plane and we can analyze, because after all rho phi and the relation between rho phi we can get from this plane, right? So we can take the point here. This is x y plane, right? This is x y plane, and this point P dash is here. What we can do here is we can draw the perpendicular on x-axis, we can draw the perpendicular on y-axis, and we can join these 2 points. This is rho, and okay, so now it becomes two-dimensional polar coordinates, right? So this is x, okay, this is y. So now you can directly write what is x here. So x is gonna be rho cos phi, right? So this is the equation number 1, and the y is going to be rho sine phi. Okay, this is equation 2. What is z? Z will be equal to z only, right? So equation number 3. Z is not changing. You can see here the z for, okay, x y g, right? X y g is the parameter for Cartesian coordinate system. So here rho and phi are the new parameters which is being introduced in cylindrical coordinate system because of the cylindrical symmetry of the structure, right? Okay, rho is the radius, and phi is basically the angle, right? And z will be same. Z will be same for both, right? Understand? So no problem at all. Now what we can do here is we can take the square of these two equations. So square 1 and 2, and add them up. Okay, so what we can do, x square plus y square is equal to rho square cos square phi plus rho square sine square phi. Okay, right? So now as we know that rho square is common here, so cos square phi plus sine square phi. Okay, so here rho equal to what? Under root x square plus y square. So you can directly tell the relation between rho. So x, y is given, so you have to find rho, right? So this is just simple relation, and phi you can directly relate. Okay, you can take the ratio of equation 1 and 2. Okay, so you will get 10 inverse, right? So take the ratio equation 1, mm, equation 2 and equation 1. Take the ratio, right? So what will happen? Y by x is equal to rho sine phi, okay, upon rho cos phi. So what you are going to achieve here is that phi will be equal to tan inverse y by x. This is the relation. Okay, this is the relation you have to keep in mind. Okay, right. So this is what the coordinate system is. Very easy coordinate system. Okay, so anyone can analyze. Right? Simple. And now we will talk about range of parameter, right? So the range of parameter, and we will talk about the locus as well. So we can also see here the unit vector for rho and all, right? So rho is increasing in this direction, so this is going to be a rho, and the phi will be like this. Okay, so phi is increasing like this, so phi is going to be this, and z will be same. So az cap, right? Az cap, because the z is not going to be different, right? Okay, the phi is changing like this. See, unit vector is defined in such a way that the quantity in which direction that quantity is increasing, right? Suppose x is increasing in this direction, so this is going to be the unit vector for x. Okay, the phi is increasing like this tangentially. Okay, so you have to okay, draw the unit vector like that. Okay, and now we will talk about the parameter, range of parameters. So rho can change from 0 to you can say infinite as well, right? So rho can change, you can say here rho can go from what? Rho can go from 0 to infinity, and the phi can, if phi is going to be constant, so the phi can go range from 0 to 2 pi. I mean, if rho is constant here, so the phi can go from 0 to 2 pi, you can say, and your z will obviously following the same minus infinity to infinity, right? So if we are using the cylindrical coordinate system, so these are the limit of integration you can take to compute the limits. Okay, integral, okay, integral, any kind of integral, right? So you can put the limit of rho. If rho is not given, if rho is given, so you have to take from 0 to 5, or okay, and phi can be taken from 0 to 2 pi. So if phi is not given, so you can pick up this 5. Okay, you can put the limit. Okay, integration d phi. Okay, so you can find here you know, phi and 0 to 2 pi, right, like this. Okay, this is the in general the range of parameter. And if I am gonna fix the rho, okay, if suppose rho is constant. Okay, so from here also the question you can expect, if the rho is constant, so what you're going to get here is the cylindrical plane. Okay, you will get this cylindrical plane, cylindrical plane. Okay, whose cross section is a circle? Whose cross section is a circle? Okay, Whose cross section is a circle? Remember, please. Let me write here properly. So whose cross section is going to be the circle? Okay. If rho is constant, if rho is going to be constant, so in the examination they might ask questions. So what kind of locus you're going to get? Cylindrical plane whose cross section is a circle, right? And whose axis coincide with z axis, remember. Okay, the z axis, it will be having the coincidence with z axis. Okay, and your arrow cap is what? The unit vector projected normal to rho equal to constant plane, right? Or you can say normal to z axis. Okay, so this arrow is the normal to z axis, you can say, if rho is constant. Okay, this is constant, so this is normal to z axis. Okay, and cylindrical axis will be coinciding with z axis. Okay, cylindrical axis will be coinciding with, so you can write here as well, whose axis coincide with z axis. Okay, with z axis. Okay, so this is what the locus here. And rho is basically what? Rho, how we measure the rho. Okay, so rho is measured normal to z axis, remember always, right? These are very important points, right? So rho is, you know, is measured. Okay, rho is a distance measured normal to the z axis, normal to z axis, right? Okay, so these are very important point, and rho is basically the distance parameter. Next, so if phi is constant, so rho can change from 0 to, all these things you need to keep this in mind, right? Because in the examination, whenever any problem is given, so you have to decide which coordinate system we have to use, right? So which parameter is going to be constant, so other parameter can vary from what range to what range, right? So suppose I'm talking about this range. Okay, so in this range, suppose rho is constant. Okay, so your phi can change from what? Your phi can change from minus infinity to infinity, right? Now we are in the second wave journey here. So you can see the phi is going to be constant in this case. Suppose phi is going to be constant. So if phi is going to be constant, so your rho can change from, rho can go from 0 to infinity. If rho is not given, so you can put the limit 0 to infinity, right? And z will be obviously minus infinity to infinity. And if we are in the third playground, okay, and one parameter is fixed again, that is on z equal to constant, okay, plane, okay. So rho can vary from 0 to infinity, and phi can vary from 0 to 2 pi. Okay, so these three playgrounds you have to keep in mind, right, while solving the integral problems, okay. In general, you know, rho can go from 0 to infinity, and I have also told you the relation, so please keep that in mind, right? Okay. See, in Cartesian coordinate system, how can you write any vector? How can you represent any vector, right? So in Cartesian coordinate system, okay, in Cartesian coordinate system, how can you write any vector? So any vector A can be written like this. The magnitude okay, and this magnitude will be sitting along x-axis. You can say ax cap, a by magnitude, okay, sitting along a by plus az magnitude, okay, cap, okay. So this is basically the magnitude here, okay, magnitude, okay, and this guy is the unit vector, remember, okay, or you can say component, okay, this is a x component along x direction, by component along by direction. So these are the components, right? These are the components, okay, or you can say the vector as well, okay. Please keep this in mind. This is in Cartesian coordinate system. And how can you write in cylindrical coordinate system? In cylindrical coordinate system, coordinate system, so a vector is there. So you can say that a rho, this is a rho component, okay, in the direction a rho cap plus b phi in the direction, sorry, a phi, okay, a phi in the direction a phi cap plus a z in the direction az cap, right? So this is again the same. So any vector can be represented like this, okay, in the three-dimensional coordinate system, okay. So this is rho component, this is phi component, this is z component. So in the examination, they will ask you what? They will ask you the conversion, okay, from one uh, from cylindrical to coordinate cylindrical coordinate system to rectangular coordinate system, or Cartesian coordinate system, or Cartesian. Suppose Cartesian coordinate system is given, and or component of Cartesian coordinate system is given, and they might ask you to determine the cylindrical coordinate system. So we will see some matrix, okay, and directly you can put those things in the matrix, and you can get the components, and you can write like this, right? Okay. So this is all about cylindrical coordinate system and Cartesian coordinate system. I hope this is understood. Okay, so in detail I have discussed. Okay, what are the range parameters and what are the locus you're going to get, right? Please keep this in mind. Okay. Yes. So now we can take few problems here. Okay, suppose any parameter is given. Suppose any one question I'm just taking here is convert these points, right? These coordinate 1, -1 and √2, okay, into cylindrical coordinates, into cylindrical coordinate, okay. Though this kind of question you can't expect because these are very easy question, school level or high school level questions, right? Okay. So this is x, this is y, and this is z. All distances are given. So you have to find rho. So what is rho? Rho is basically x square plus y square. You can plug here simply, and 1 plus -1 whole square. So this will give you √2. And you can find phi. Phi will be what? Tan inverse by x, right? 1 by -1 -1 by 1. So this will give you -45 degree. Okay. And z also you can find. So z will be same, right? So z will be √2 only. So this is how you can compute. So normal question. Okay. And suppose any question number 2 is from here this kind of question you can expect, and also questions from the locus. Okay, if any point is fixed, so what kind of locus you're going to get, right? The cylindrical core, cylindrical plane, or if phi is fixed, then what kind of locus you're going to get. So if phi is fixed, then the cone you will get, right? So all these things you have to keep in mind. Suppose convert question is like convert 2 pi by 3 and 1. into Cartesian coordinate system. Okay, so just to recall those formula which we have studied. So this guy is rho, phi, and g. So one angle is there and this, right? So x can be found out like rho cos phi. So this will be 2 cos 2 pi by 3, right? So this is going to be your -1, and pi equal to rho sine phi, right? So again here you will get as it will be giving you what, root 3, right? And z will be equal to 1 only. Okay, so this is how you can find out. Now you need to know what is cos 2 pi by 3 and all, sine 2 pi by 3. So please take care of that, right? So how we can convert any Cartesian coordinate system into cylindrical coordinate system? That is very important, right? Suppose A is given as ax cap, a by cap, az cap, right? Suppose they are asking you to convert this. This is cart, right? And they are asking you to convert into cylinder. Okay, cylindrical. So how can you convert this, right? So here a rho cap, right? A phi cap, az cap, right? So this conversion, how you can go from Cartesian to cylinder and the cylinder to Cartesian, right? So that's what I'm going to talk now. Okay, so please keep this in mind, one matrix, and where you have to keep. So in the IES subjective also questions are asked from this topic. Okay, so I hope you will be able to. So the topic will be, what topic is going to be your conversion of Cartesian coordinate system into cylindrical coordinate system, right? Conversion of Cartesian coordinate system into cylindrical system. Okay, so conversion of Cartesian coordinate system into cylindrical system. So suppose any x, y, z components are given, right? So ax component is given, a by component is given, and az component is given, right? And you have to find a rho, a phi, and az component, right? What you have to do here is you have to put a rho, a phi, az here, and one matrix will be there, right? Which where the input has to be given, right? Okay, and here you have to put, means you have to introduce this ax, a by az. This is like this. Okay, suppose ax, a by, and az components are given, so you have to give these components to this matrix. Okay, conversion matrix, right, to the input here as an input, and you will get output as, so this is going to be your input and this is going to be your output, right? So this matrix will convert directly. Okay, so you don't have to bother about any geometrical way of understanding how they are converted. So ax, ay, az, you need to only keep in mind this matrix. Okay, so in the input you will give these components, and matrix will convert these cart component, right? These are the cart component, you can say. So output is gonna be your cylindrical a rho, a phi, and az, and vice versa. Okay, and vice versa, right? Vice versa is also some different matrix we will see, right? Okay, transpose of that. So let me write here. So here the component is gonna be ax, ay, az, This is your input, okay, Cartesian components. So what you can do here is you have to write cos phi here, right? Cos phi, sin phi and 0, minus sin phi, cos phi and 0, and this is 0, this is 0, this is 1. How can you remember this, right? How can you remember this? So if there is a cos, right, so you have already got x equal to rho cos phi, okay, by equal to rho sin phi, right? What you can do here is you have to keep this, you have to take cos here, right, and then you have to keep here sin phi on 0, right? So and next one is going to be what you can differentiate this. So cos phi differentiation is going to be what? The cos phi differentiation is going to be minus sin phi. So you can see here cos phi equal to minus sin, cos phi differentiation. So you can differentiate this sin phi differentiation, you will get the cos phi here, right? And this. So only thing is from the Cartesian and polar or cylindrical parameters, what are the relation here? X equal to rho cos phi. So drop the drop rho parameter, write only cos phi here, sin phi 0, okay, then differentiate this, okay, horizontal vertically you can say. So let me write again so that you could keep in mind. So this is a rho, a phi and a z, right? They are the output, right, which I'm gonna get, and the matrix where the input has to be given to this matrix. So here ax will be given, a y will be given, az will be given. So how can you remember, what are the elements which will be here, help you to get cylindrical coordinate system? So you know the equation x equal to rho cos phi, okay, and the y equal to rho sin phi, okay. So what you can do here is you can drop this rho parameter, just forget about this rho, and put here cos phi, okay, put here sin phi, and you can put 0, right? Cos phi, sin phi 0, okay. Now what you can do here is you can differentiate this. So what is the differentiation of cos phi? So dy by d phi cos phi. Cos phi differentiation is giving you the negative one, that is minus sin phi, okay, and sin phi differentiation is going to be cos phi, right, and 0 means 0, right, and here it will be 0 0 and this is 1, okay. And this is how we remember, right? So if you will input the Cartesian coordinate system component, so you will get the cylindrical coordinate component, right? Okay, and you can take the transpose of that. So suppose the system is like a rho, a phi and az is given, right? This is given, okay, and there is a matrix. So what you're going to get here is you will get ax, ay, az. So if this is how you will study, so you can keep everything in mind. So this is the input here this time, and this is the cylindrical component, right? Cylindrical component is given, okay. And now if you will give the input here, the matrix is going to be converting into the what we can say cart component, right? And component, if component is given, you can put the unit vector and write the vector format, right? Okay, right. So we'll solve few problem as well. So what matrix that? So take the transpose of that. So if you have to find ax, ay, az, so whatever you have to find right here, okay, and just take the transpose of that, right? So this is gonna be your a rho, if a rho, a phi, az, right? And take the transpose. So what you can do here is this is cos phi and this is sin phi and this is 0. Now differentiate this cos phi, right? So the cos phi is going to be your sin phi 0 and sin phi differentiation is cos phi 0. Only you need to write the first column of this matrix and rest is so this is Okay, so this is the input which you have to give here. This is going to give you, combining the two is going to give you these Cartesian components, right? So let us take few problem here. Okay, so the problem, these problems are also have been asked in IES subjective papers and IES objective. In HAL also they can give you, but the importance of these discussion, the discussion of coordinate system, static, magnetostatic. In fact, and the plane waves, antenna, transmission line, waveguide, everywhere, we will talk about differential length and differential volume and integral calculus, right? So find the space coordinate, right? So understanding of these coordinate systems are very essential, right? Okay, so these are the prerequisite which we are discussing. So in the examination they have given here the convert, okay, convert vector A, okay, minus x A by cap plus z Az cap, right, into cylindrical, right, into cylindrical, okay, coordinate system, right? So what you have to do here is you have to find basically the A row, A phi and Az, right? And there is a matrix which I have told you, so you have to write that matrix, and here is given. Situation is what? This is the x component, this is y component, this is z component. So you can write here, this is y component, this is minus x, and there is a z. And you can write horizontally, okay, that is cos phi, sin phi, right, and 0. Now differentiate vertically, right? So minus sin phi, this is cos phi, and this is 0, and 0, 0, 1. So now you can multiply, I think multiplication is easy, okay? This is 3 cross 3 and this is 3 cross 1. So what you're going to get here is, we can say that A phi, okay, A phi component you can get from here. So A phi will be what? By times cos phi, by times cos phi, okay, minus x times sin phi, okay, and rest is 0, right? So in place of x by, what you can plug back rho cos phi. Okay, in place of phi x, because you have to write purely in cylindrical coordinate system. So rho cos phi you can plug here, and by equal to what? Rho sin phi. Okay. So a row component will be what? A row component will be rho sin phi cos phi, okay, minus, after get plugging back these x and y values, so rho cos phi here and sin phi. So if you see here, this is coming to be 0, okay, and a phi also you can compute. So a phi is going to be what? A phi, you can see a phi will be minus sine minus by times sin phi and x times, right? So this will be equal to minus something. So directly writing sine square phi minus rho cos square phi, right? So here you will get minus rho, right? And Az is equal to z only, right? Az equal to z, okay? So now you have got the component, right? So A row component 0, A phi is this, and Az is this. So how can I write now? So A vector can be written as 0 dot A row cap minus rho A phi cap plus Z Az cap. So this is going to be your answer, right? So how easy this is, okay? If you understand, like you are inputting any kind of coordinate system to the matrix, conversion matrix, and you're getting a desired coordinate system, right? in the vector format. Okay. So I hope this is clear for everyone. This is very important discussion, right? So please keep this in mind. Right? Whatever I am discussing here, you can see. Please keep this in mind. Okay. Right. So let us go to next problem, because problems are very important, right? So these are the tools which will be used to discuss entire electromagnetic. Okay. So suppose question is given here, convert A is given, right? By AX cap plus A by cap plus x square under root x square plus y square, AZ cap. Okay. Suppose A vector is given like this, and you have to convert into A rho A phi AZ, right? So what you can do again is, this is the AX component, and one is the component here, and this is the Z component, right? So again you have to plug. Okay. So using that matrix, I think you can do this problem. So this is gonna be your homework. So you can do this, right? So in place of x, what you can do here is you can plug, you can take the help of rho cos phi. Okay, x equal to rho cos phi, and you can also take the help from by, that is rho sin phi. Okay, so you can place here, right? You can place here, so you will get a simplified version. Okay, it is gonna be very easy, right? Now let us take one problem which cylindrical to Cartesian is asked. Okay, so in the question they have asked convert the any cylindrical coordinates vector, right? The vector representation given in cylindrical, that is minus rho A phi, okay, A phi cap, yes, and plus Z AZ cap into Cartesian. What you can do here is the AX equal to rho sin phi. Okay, wait, let me erase this. Okay, so this is very easy. Okay, so this time the cylinder is given, cylindrical coordinate system is given. So this is a component, phi component, this. So A rho component is 0, A phi component is minus rho, and AZ component is Z. What you have to find here is you have to find AX A by AZ, right? So this time you have to put the matrix again, and here the input is 0 minus rho Z, right? So what you can do here is you have to take the transpose of that matrix which we have studied. So here you can say this is cos phi, okay, and this is sin phi, and this is 0. And now differentiate, this time horizontally. So this is minus sin phi, and this is cos phi, okay, and this is 0, and this guy is 0, 0, 1. So it is very easy now, right? So rho sin phi you will get as x. Yeah, rho sin phi. So AX you are going to get here is rho sin phi, okay, which is equal to by only, right? And A by you are going to get here is minus rho cos phi, okay, which is equal to x, and AZ is going to be Z, right? So the vector A can be written now along with the components and the unit vector, that is by AX cap minus x A by cap plus Z AZ cap. How easy this is, right? So remember that input, give input to the, the conversion matrix, and you will get, right? Okay. One of the question asked in the IES subjective paper, right? See, I'm just giving you. The question was like convert convert A vector equal to A rho cap, right, into Cartesian, right, into Cartesian at P111, right? So just what was given here, the rho component is given, right? So what you have to do here is you have to find the AX component, you have to find A by component, you have to find Z component, right? And what you can do here is you can write the matrix. This is cos phi, sin phi, 0. Now minus sin phi, right? Let me write properly here. Minus sin phi, right? And this is cos phi is 0 and 0, 0, 0, 0, 1. Right? So, and what are the component? Rho component 1 by rho is given and rest of them is 0, right? Okay. So now you can see directly here, anyone can solve this kind of a question, right? So for, suppose this is AX. What is AX here? That is 1 by rho cos phi. Okay. And so how you can write this as? So you know that x equal to what? Rho cos phi. Okay. Rho cos phi. Understand? So you can replace this cos equal to you know, cos phi equal to what? That is x by rho. And what is rho equal to under root x square plus y square? So just keep here, right? So you will get here as x upon, rho square means x square plus y square, because you will get here as what? You will get as x upon rho square. So you can write like so. Ax you have got here. Ax is equal to x upon x square plus y square. And similarly, you will get a by component as well. So a by component, right? Not vector, just component I'm writing. So a by component you will get as the by upon x square plus y. Very good problem, right? And az is 0, so az is 0, right? So easily you can write here. Now what you can do here is they are asking at P111, right? 111. At P111, 111, right? So what you can do here is you can say that AX component is going to be 1 by 2 and A by will be also 1 by 2 because 1 upon 1 by 2, right? And AZ is going to be 0. So your answer for this question will be what? This is in card half common, AX cap plus A by cap. Very beautiful problem this was, right? This problem was asked in IS subjective, right? Okay. So I hope this is clear for everyone, and please make sure that everything is understood. Okay, right. So let us discuss about spherical coordinate system as well. Spherical coordinate system. Okay, so today's discussion is gonna be on coordinate system only, right? So we have discussed about Cartesian coordinate system and application of them, and in case of cylinder, if you're going to take the point on the cylinder, and so the coordinate system will be different, right? The direction is going to be changed, but in case of Cartesian there was no restriction at all, right? Anywhere you go along x by z, the direction is going to be same, right? So in case of spherical coordinate system, this coordinate system will be used to analyze antenna problem, remember? Okay, antenna problems, right? So what we are going to do here is in case of spherical coordinate system, right? we'll consider one octave, one octant, right? So this is one octant, right? One simple octant. Okay. So in Cartesian coordinate system, the reference point was the, reference point was what uh, we have just, any point in the space, right, will be the reference. Any point in the space, right? Any point in the space is the reference point, right? In case of cylinder, we started with the axes, right? Cylindrical axes. Here, what we are supposed to do here is that we will take one octant of the sphere, right? So let me draw properly this. Just draw one octant. This is one octant, right? Spherical. Okay, right. So let me erase this and draw again. So we will always take the help of Cartesian coordinate system x, y, g, and this is just one octant, right? You can say. And now what we have to do here is we have to cut this cylinder, right? Just cut this cylinder like this and take one point P here, right? So the not cut this spherical, okay? Spherical. If there is a spherical symmetry, so we need to find the parameter of a spherical coordinate system. So you have to cut it, right? You have to cut like this and just take the point P here, right? What you can do here is you can just take this point P here, no problem. So you can join this point P, and the angle which it makes from the z axis is theta, and the distance from this origin, okay? So you can you can locate origin at any point on the sphere, right? Because uh, this is the reference point, right? We don't know where is the exact origin in the sphere, right? Sphere is the inverse, you can say, right? So just take like this, okay? And you can take the projection, this projection of this, okay? So P dash is here, join here, and the angle which it makes from the x-axis is phi. So the P is basically coordinated as r theta phi, okay? R theta phi, right? Okay, r theta phi, okay? Remember, okay? This is very important for the spherical coordinate system, or phi theta, whatever you wanna call it, right? R theta phi or phi theta, you can say, okay? So P will be coordinated as r phi theta, okay? Right, r phi theta. So how we are getting this? Let me again draw. So this is x. Let me draw. Let me take that line. Okay, so this will be very good. So this is the x. This is z axis. Sorry, y axis, right? And there's gonna be your z axis, right? And this is gonna be your x axis, right? Okay. Now there is one octant. These are the octants. Okay. Now what will happen here is that you have to cut this cylinder like this. You can just cut like this, okay? From originating from z axis, originating from z axis, right? So like this, and okay, and just take the point P here, right? And join this point P from this to this. So this is going to be your theta, and this is r. And take the projection of this guy in the xy plane, okay? So here is the P dash, join this and make this as a phi, okay? So this P is coordinated as R phi theta, R theta phi or R phi theta, okay, the way you want to write, okay, R theta phi or R phi theta, okay, no problem. So now you can see here, this is going to be the unit vector along R, and this is going to be the unit vector along theta, okay, and phi is varying like this, right? So this is going to be this phi, okay. So these are the coordinate okay parameters for spherical coordinate system, right, or phi theta, right? And if I talk about the range of the parameters, right, the range of the parameters here, range of the parameters. So range of the parameter is going to be what range, what is the parameter here? That is R, you know, R theta phi or R phi theta, R theta phi you can write here. Okay, so R is ranging from what? R can range from 0 to infinity, and theta can be range from you know 0 to pi, and your phi can go from 0 to pi, right? This is the range, okay? And remember always, theta can go from 0 to pi, and if R is constant, if R equal to constant, if the if R is equal to constant, so what kind of locus you're going to get, right? So locus you will get here as the sphere whose center is at origin. What you will get? Sphere whose center, okay, whose center is at origin. Is at origin. If you can say phi is going to be constant, if phi is going to be constant, so the locus is going to be what? Locus will be half plane originating from the z axis, half plane originating, right, from, okay. So I guess in cylindrical coordinate system I said phi equal to constant means okay, so it was like in my mind, you know, a spherical coordinate system was going on, right? So there was phi, right? Phi equal to constant as well in case of cylindrical coordinate systems. You have to understand that the locus is going to be the half plane originating from z axis, right? With an angle theta, okay, to zx plane. Remember. Now, and theta equal to constant means what? What locus you will get. So now it is correct. Theta equal to you know constant means the locus you will get it as a circular cone, right? Circular cone. So please keep this in mind. In case of rho equal to constant, it was a circle, right? In case of phi, the plane will be originating from z-axis, remember, right? And theta here, if theta equal to constant, right? In a spherical coordinate system, you might have observed that you have got two angles and one distance, right? So the theta equal to constant means locus will be what? Circular cone, okay? With x-axis, with x-axis as it is symmetrical, symmetric axis, right? As not x-axis with z-axis, right? So this kind of locus you will get, okay, this kind of. So the z-axis is the symmetric axis, right? Circular cone with z-axis as it is symmetric axis, right? Okay. So theta equal to constant is very important. This guy is very important, right? So in the examination, they might ask locus as well, right? Please keep this in mind. Okay. Okay. So if I talk about the relation between you know, spherical and Cartesian, right? Spherical and Cartesian. What relation you have got here is that, as we know that we can prove or you just write it, right? So x will be equal to, basically, as we know that x equal to what, rho cos phi. So you can in place of rho, and rho can be determined from here, right? Rho can be determined from here. So what is rho here? This is rho, right? So now rho will be what? Rho can just join from here. This is rho, right? And the rho will be basically r sine theta. Okay, rho is going to be in from this triangle. Okay, you can find. Okay, rho will be what? Rho will be equal to r sine theta. Okay, and z will be r cos theta, kind of. Okay, so let me write here. Yes, so in place of rho, you can place r sine theta cos phi. So this is the equation number 1. And as we know that bi equal to rho sine phi, so rho is again r sine theta sine phi, right? So this is equation number 2, right? So you have got equation 1 and equation 2, and z is basically r cos theta, right? From here, only from that triangle, uh, you can compute z equal to r cos theta. Right? So let me put here z equal to r cos theta. This is equation number 1. What you can do here is you can square 1, 2, 3. You can square 1, 2, 3. Square 1, 2, and 3 and add them up. Okay. What you can do here is now squaring. So x square plus y square plus z square will be equal to, okay, r square, r square sine square theta cos square phi, r square sine square theta sine square phi plus r square cos square theta. Okay. Now you can see here from this to this, okay, from this and this term, okay, you can take common as sine square theta, right? So taking r square theta and sine square theta, right, common, okay, from both. So r square and sine square theta is common here. So it will be equal to cos square phi plus sine square phi, okay, plus r square cos square theta. So this is the identity, okay, which is going to be giving you 1. And now what you can do here is r square take common here. So r square will be equal to what? Sine square theta plus cos square theta, right? So you can say this is r square. Okay, so now what relation you have got here is that r square equal to what? Under root, not under root here, it will be x square plus y square plus z square. So what you can say, r equal to what? R equal to x square plus y square plus z square, right? Please keep this in mind. Right? They are squares, please. Okay, because I'm speaking as well and I'm writing. So this is the conversion. This is the relation between x, y, z, and r. Please keep this in mind. Now, what you can do here is you can find theta directly. So theta is going to be what? Theta will be equal to cos inverse g by r, right? Here r is, you know, that x square plus y square plus z square. Okay, this is z because z equal to what? In case of sphere, z is equal to directly we have seen from the triangle z equal to r cos theta and rho equal to r sin theta. And phi also will be same. Phi will be tan inverse y by x. So these are the relation which we have to use. Okay. So let us take one numerical problem just to realize. Okay. So the coordinate is given as 2, -1, and 3. Okay. So this, by looking at the coordinate, you can identify there is no angle, right? So it is given in Cartesian and you have to convert into spherical coordinate system. So we'll take up in the next class few problem, okay, which has recently been asked in gate examination, right, from these concepts. So combining these knowledge, whatever the knowledge we are getting from this session, right, we will be using. So spherical coordinate system, these are the points. So how to convert point from one coordinate system to another is also very important because sometimes they will ask different the distance between 2 points. Okay, so if they will give you spherical coordinate in the spherical coordinate system, right? So then converting into uh, converting into this Cartesian and then finding distance will be easy as well. We'll see. Okay, once upon a time that question was asked. So yes, how can you find r here? R will be equal to r phi theta. You have to find. So r is gonna be just 4. Okay. So r theta phi. So this is 4. Okay, because this square plus 1 plus 9. What you're getting here is that it is 14. Approximately 3.74, right? And phi you can get here from tan inverse -1 by 2. So it is in degree, you will get as -26.56 degree, and theta will get from cos inverse z by r, right? So this you will get as 36.69 degree. Okay, so this is very important to keep in mind, right? So limits I have told you for various uh, r and that, right? So this r can go from 0 to infinity, but capital R, if in the question they have given, right? And your theta can vary from 0 to pi, and your phi is happy going, right? 0 to 2 pi. Okay, so these are parameters you have to keep in mind. So conversion of Cartesian to spherical, how can we write here, right? Suppose again conversion of card to spherical. Okay, so suppose in the input they are given ax a by az, and there should be a matrix, right? Conversion matrix. What you are going to get here is this is input, right? So what you're going to get here is the spherical. So you will get spherical component, right? This is the card component, remember. Okay. So let me write here. So you have to find what? You have to find mm, uh, you can say anything, right? So what is given here is that the card component you have to find. Okay, so here you can write AR, A theta, and A phi, because R theta phi is the coordinate system. R theta phi. Okay, R theta phi is the coordinate system here, and the conversion matrix element will be here, and what is given, the component of x is given here, so ax a by az. How can you write here, right? So as we know that x is equal to what? Rho, sorry, x is equal to r sine theta cos phi, right? R sine theta cos phi. What you can do here is that you can pick up, you can drop this r, just drop this r, right? Just take this guy and write here. Okay, so sine theta cos phi, here write sine theta cos phi. Okay, and then in next that bi is equal to what? Bi equal to r sine theta sine phi, right? What you can do here is again drop r, sine theta sine phi, sine theta sine phi, and 0. Not 0 here, there will be uh, z component, because z component is also present, right? So there is a z1. Z is what? Z is equal to r cos theta. Please write cos theta here. Okay, very good systematic way of writing. So let me write in the next page because you might find it cluttered. So let me write here that is AR, A theta, and A phi, R theta phi. Okay, and here we can write sine theta cos phi, sine theta sine phi. Okay, and cos theta. Now what you can do, you can differentiate the first one with respect to theta, so it will be giving you cos theta cos phi. You can differentiate this as well, so it will give you cos theta sine phi. Very good. Okay, and now it will give you sine minus sine theta, and now differentiate with respect to phi. Okay, so and leave this theta. Okay, leave this theta. So what you have to do, differentiate with respect to phi and leave, forget about this cos theta, right? So it will give you sine phi, and it will give you cos phi. Just it is a trick to remember cos phi, and this will give you 0 because there is no phi component, right? I mean there is no phi term, understand? And this is ax a by and az. Okay, so this matrix you have to remember, this matrix. Once you know this matrix, just give the input here and you will get this guy. Okay, and suppose the condition is like this, the matrix is here, right? I mean we are conversion matrix, and you have to give input as ax a not ax a by az, a ar a theta a phi. So you have to get ax a by and az, right? So what you can do now here is you will have to write, you will have to take the transpose of that, right? So here you have to find ax a by az, and here you have to go for the conversion matrix, right? So sine theta cos phi. Right? Then vertically you have to write cos theta cos phi. Okay, not this is sine phi was there, no? Just avoid, I mean remove this guy. Sine theta sine phi. Okay, and cos theta. Okay, put like this. Now differentiate horizontally. Okay, with respect to theta, so it will be cos theta cos phi. Okay, and this is gonna be your sine theta differentiation means cos theta only. Cos theta sine phi, and cos theta is minus sine theta. Now differentiate with respect to phi and forget about this cos factor, right? Cos theta. So what will be here? Minus sine phi, and this will give you cos phi, and this will be 0. AR, A theta, A phi. Very easy, right? Or take the transpose of that. Okay, transpose of this. Understand? I mean the given matrix, the first matrix. Okay. So this is what I wanted to discuss, and you can remember also the conversion from spherical to cylindrical, right? Conversion from spherical to cylindrical. Okay, these are very important concepts. Okay, many of you might. So if cylindrical components are given, and you have to find the spherical coordinate system. So again, the matrix you need to keep in mind. So you can say A rho, A phi, and AZ, and here you can write AR, A theta, A phi, R theta phi, rho phi G. This is a sequence, right? R theta phi, rho phi G, x by G. Okay, that is a sequence of the parameters. So this is sine theta 0, cos theta 0 minus sine theta. Okay, so you can differentiate sine theta and you will get minus sine theta here, and 0 1 0. So only you have to keep this in mind, and you will go ahead. Understand? Right. So this is what I want to discuss today. In the next class, we will be talking about differential length, area, volume. Okay, and we will try to discuss various problems, right? So we will discuss about del operators. Okay, and del operators. Okay, we'll talk about gradient, divergence, and curl. Okay, we'll talk about vector calculus. So tomorrow will be our prerequisite. These are the prerequisites, right? Prerequisite. Okay. So within 2 classes, we will understand the prerequisite and solve problems. The question will be definitely asked from these prerequisite as well. Okay. And then we will briefly discuss electrostatic, magnetostatic, and within 5 to 6 classes we will summarize everything. I hope today's session is might have been interesting, right? And you have to remember this sequence, r theta phi sequence, right? R theta phi sequence, r theta phi sequence, okay? R theta phi here, correct this, r theta phi, okay, r theta phi sequence. Okay, let me erase this and write properly. R theta phi sequence, r theta phi. Okay, because after r you are getting theta, then phi. So thank you so much. We will meet in the next class. Thank you.